Hi to everyone. In this video, I would like to explain about system response. Second one is mean and mean square value of system response. And next one is autocorrelation function of response. And the last one is cross correlation functions of input and output. In my previous videos, we have observed that the mean and mean square values, autocorrelation function and cross correlation function of either x of t or y of t. Now, when we are going to apply this x of t as the input, we will get something response. For that, what are the different parameters are there that I will explain in this video. In that, the first one is system response. What is meant by system response? Let us observe this block diagram. This is x of t is the input and y of t is the output. I am going to apply this to the block whose transfer function is nothing but h of t. H of t is also known as the impulse response. If you apply x of t to the system which is known as LTI system, LTI stands for linear time invariant system, we are going to obtaining y of t. Then what's the equation of that system response y of t? Y of t is equal to integral minus infinity to infinity h of tau x of t minus tau d tau. We can observe that this formula is nothing but convolution. Therefore, y of t can be written as simply y of t is equal to h of t convolution x of t. That means the output response is equal to the convolution of, this is the impulse response of the system and this is the input. That's why convolution of impulse response and applied input. This is the definition as well as equation of the system response. Next, coming to the mean value of system response. Y of t is equal to h of t convolution with x of t. To calculate the mean value, we have to apply the expected value. Therefore, E of y of t is equal to E of this entire function, that is h of t convolution with x of t. Now, substitute this convolution formula here. We are going to obtaining as E of integral minus infinity to infinity h of tau x of t minus tau d tau. Now apply this expected value to the random process x of t minus tau. Therefore, this equation is equal to integral minus infinity to infinity h of tau into E of x minus t minus tau into d tau. Here you can observe that E of x of t minus tau is equal to simply x bar for the case of WSS process. WSS stands for wide sense stationary. For that case, the mean value is constant, that is equal to x bar. Substituting this x bar here, we will get as simply E of y of t is nothing but equal to y bar, that is equal to x bar. Since it is a constant, you can write this out of the integration. So, x bar into integral minus infinity to infinity h of tau into d tau. Now, we can define h of omega. If h of t is the impulse response, then h of omega is the Fourier transformation of h of t, whose formula is given as h of omega is equal to integral minus infinity to infinity h of tau into e power minus j omega t dt. At omega is equal to 0, h of omega will become as h of 0 is equal to integral minus infinity to infinity. This will become as h of t, e power 0 is nothing but equal to 1. So, simply it is equal to integral minus infinity to infinity h of t only. That means this is nothing but the h of omega value at omega is equal to 0. Now, in the above equation, we are having the same term. Substituting that there, we are going to obtaining as E of y of t is equal to y bar is equal to x bar into, instead of this entire you can substitute as simply h of 0. Substituting this here, we will obtain as x bar into h of 0. X bar is a constant, h of 0 is also constant. Product of two constants are equal to constant only. That's why the mean of system response, that is E of y of t or y bar, is also a constant. Then coming to the next one, mean square value of system response. Y of t is known as the system response. Its mean square value is given as E of y square of t. That is equal to E of, substituting y of t value, which is nothing but equal to convolution of h of t and x of t. For that whole square, we are going to writing. Then the next step, for this whole square you can written as simply E of h of t convolution with x of t. One more time we can write as in whole into h of t convolution with x of t. In terms of integration, this convolution formula can be written as E of integral minus infinity to infinity h of tau 1 into x of t minus tau 1 d tau 1. This is for the first convolution. For this case, we are writing this. And for the second convolution, we are writing this one. That is integral minus infinity to infinity h of tau 2 into x of t minus tau 2 into d tau 2. This is nothing but for the two different cases we are going to taking. Now rearrange the terms, we are going to getting as expected value of two integrations are there here. Right here integral minus infinity to infinity, integral minus infinity to infinity. Then write the random processes x of t minus tau 1 into x of t minus tau 2. Then impulse responses here what you are having, this is h of tau 1 and this is h of tau 2. These two here we are going to writing, and then d tau 1, d tau 2. Like this it is simplified. Then here you can observe that applying the expected value to the random process. Therefore, E of y square of t is equal to integral minus infinity to infinity, integral minus infinity to infinity, expected value of E of x of t minus tau 1 into x of t minus tau 2 whole into the impulse functions h of tau 1 into h of tau 2 into d tau 1 and d tau 2. Now here you can observe, to simplify further, see this function E of x of t1 minus tau 1 into x of t minus tau 2. That can be further simplified as, this is nothing but simply the autocorrelation function at tau 1 minus tau 2. That means the entire expression can be replaced with simply Rxx of tau 1 minus tau 2. Therefore, by substituting this in the previous equation, we are going to obtaining E of y square of t is equal to double integration of minus infinity to infinity. This can be replaced here with Rxx of tau 1 minus tau 2 into h of tau 1 into h of tau 2 into d tau 1 d tau 2. This is the equation for the case of mean square value of the system response. Here you can observe that there is no any either t1 or t2. All is the consisting of only tau 1 and tau 2. Tau is nothing but it is the difference of time t1 and t2. That's why the mean square value of the system response does not depend upon the time. It is depending upon the time difference tau only. Hence, it is also a constant. That means mean and mean square value of system response both are constant only. Next topic is autocorrelation function of system response. System response is indicated as y of t. Then its autocorrelation function is Rii of t1 t2. The respective formula is expected value of y of t1 into y of t2. In this, substitute the expression for y of t1. Y of t1 is the convolution of h of t as well as x of t. Therefore, this can be written as e of h of t1 convolution with x of t1. Similarly, y of t2 we are going to writing as h of t2 convolution with x of t2. For this y of t1 we are going to using here as t1. For this y of t2 we are going to using here as t2. Now, writing in terms of integration, this can be written as expected value of integral minus infinity to infinity h of tau 1 into x of t1 minus tau 1 into dt1. For this case, we are going to writing this. Our next convolution formula in terms of integration is integral minus infinity to infinity h of tau 2 into x of t2 minus tau 2 into d tau 2. For this case, we are going to writing this entire expression. Now, rearranging the integrations, this can be written as expected value of double integration of minus infinity to plus infinity. Arranging the x terms here, x of t1 minus tau 1 into x of t2 minus tau 2 whole into h of tau 1 into h of tau 2 d tau 1 d tau 2. Now, apply expected value for this random process x of t. Therefore, this can be written as double integration of minus infinity to plus infinity expected value of x of t1 minus tau 1 into x of t2 minus tau 2 into h of tau 1 into h of tau 2 into d tau 1 d tau 2. Now, here you can observe this expected value of the random process at two different times t1 comma t2 can be represented as simply rxx of t2 minus t1 plus tau 1 minus tau 2. Whatever here we are having this entire minus this one, then simplified can be written as like this. Therefore, that can be simplified as further simply rxx of tau plus tau 1 minus tau 2, where tau is nothing but difference of t1 as well as t2. Substituting this in the previous equation, then we are going to getting as ryy of t comma t plus tau is equal to, here you can see only tau is there. That's why this can be simply written as ryy of tau, that is equal to double integration of integral minus infinity to plus infinity, this rxx of tau plus tau 1 minus tau 2 into h of tau 1 into h of tau 2 d tau 1 d tau 2. Here you can observe that if x of t is a random process and rxx of tau is the autocorrelation function of the random process, then autocorrelation function of the output y of t or system response is nothing but, observe this equation. This is the double convolution formula which can be written as rxx of tau convolution with h of tau convolution with h of minus tau. Here you can observe that one is having plus tau 1, other one is having minus tau 2. Hence, we are having the double convolution, one is with positive, other one is with negative. Therefore, autocorrelation function of system response ryy of tau is equal to rxx of tau convolution with h of tau convolution with h of minus tau. Coming to the next topic, that is the cross correlation function of the system response. The cross correlation function is indicated as rxy of t comma t plus tau. If x of t and y of t are two random processes, then their cross correlation function is given as rxy. Hence, we are indicating as rxy of t comma t plus tau. That is equal to, the general formula is e of x of t into y of t plus tau. Now, writing the what is expression for y of t plus tau? Therefore, this is equal to e of x of t as it is you are writing. This is nothing but the convolution formula because it is the system response. That can be written as integral minus infinity to infinity h of tau 1 into x of t plus tau minus tau 1 into d tau 1. Writing as in terms of convolution, then in terms of integration, we are going to obtain like that. Now, rearranging the terms, that can be equal to integral minus infinity to infinity e of x of t into x of t plus tau minus tau 1 whole into h of tau 1 into d tau 1. Now you can observe this term, expected value of x of t into x of t plus tau minus tau. This is nothing but equal to simply r xx of tau. Therefore, you can see that here r xy of tau is nothing but equal to the convolution of r xx of tau with h of tau. Therefore, the cross correlation function of x of t and y of t is equal to simply convolution of autocorrelation function of the applied input x of t and the impulse response h of t. Similarly, we can write one more cross correlation function, that is r y x of tau is equal to r x x of tau convolution with h of minus tau. Simply replacing this x and y, that will become as r y x. Therefore, here instead of plus tau, we are going to obtaining as minus tau. So, this is about the cross correlation function. Here you can see once again the expressions for the cross correlation functions are there here. So, thus in this video I have explained about the mean value, mean square value, autocorrelation function and cross correlation function of input and system response. Thank you.